All right, this is the last lesson of our log unit. Today we're going to be solving logarithmic and exponential equations. We're going to start with exponential equations. We want to know for what value of x is this equation true? We have 3 to the x power equals 50. Well, we want to get the x by itself. We want to have x equals something. And the strategy that we're going to use to solve for x is the strategy of rewriting an exponential equation as a log. So right now we have something that very much looks like this. We have 3 to the power x equals 50. We can rewrite that as a log, and if we rewrite it as a log, it becomes that the log base 3, so whatever base you're in, that base becomes the base of the logarithm. And in the case of this equation, it would be log base 3 of 50 is equal to x. When you rewrite it, that exponent becomes the answer, or the right side of the equation, and the equal sign up here, what the exponential is equal to, becomes the argument of the log. So we have log base 3 of 50 is equal to x. And really, that is what x is equal to. X is equal to the log base 3 of 50. Sometimes you'll see the answers left in that form, like on the ACT, they may leave it in that type of form. It's just in a logarithmic form. But we could also figure out what that number is approximately, a decimal approximation. To find that decimal approximation, we would use the change of base formula that we talked about last time, which said that if we have log base b of a, that's the same as the log of a, which is now base 10, divided by the log of the base, but now that's a base 10 log. So by using this change of base formula, we can use our calculator to evaluate this log. So this would be the log of 50 divided by the log of 3. And if you put that into your calculator, remember that in most calculators you will probably have to make sure that you are entering it carefully. So this would tell us that x is about equal to 3.56. And that would just be a rounded decimal approximation. This would be considered an exact answer. There are questions on your test that would ask you to get a decimal approximation. So if you have questions about when you're supposed to do which, you can ask me. For the questions that we're working on today, we're going to go ahead and get the decimal answers. But there are times when it would be okay to leave it in that exact logarithmic form. Okay, so we're going to use that same strategy to solve exponential equations. We may have to occasionally, though, work with our equation first before we convert it into a logarithmic equation, but it will just depend on the equation. So this first one, 2 to the power x minus 4 is equal to 100. We can go ahead and rewrite that as as a log equation right now. Our power is x minus 4, but that's okay. That's just going to become the right side of the equation when we rewrite it. So it'll be a log, and this time base 2 of 100 is equal to x minus 4. Log base 2 of 100, if we use our change of base formula, that's the log of 100 divided by the log of 2. And if we calculate that amount, log of 100 divided by the log of 2 is about equal to 6.644. and that's equal to x minus 4. So to solve for x, we would just want to add 4. So we get 10.644 is equal to x. So this next equation in some ways is very similar. We have an x plus 2 as our exponent this time. Maybe what's different here is you notice that this has a plus 3. And because that has that plus 3, we're not ready to rewrite it. We need the equation to look like this form where we have an exponential. We've got the base raised to the power equal to something. And right now we have this plus 3 that is not in that form. So we're going to go ahead and first, before we start rewriting, we're going to subtract the 3. So we have 5 to the x plus 2 power is equal to 22. And now it's in that form, and it's going to be very similar to the problem that we just did. We're going to rewrite it as a log, so it's going to be the log base 5 of 22 is equal to x plus 2. Remember that the power of your exponential becomes the answer to the logarithm. Log base 5 of 22, if we do change of base, would be the log of 22 divided by the log of 5. Which is 1.921. That's still equal to x plus 2, so to finish up the problem and solve for x, we just need to subtract 2. So we end up with the solution that x is equal to negative 0.079. So we'll get a wide variety of answers as we're doing these types of equations. Okay, now a couple that are base E. This first one, I want to talk about what this is really saying. As it's written here, sometimes people get confused and they think that it means this. They think that it means that 40 is part of the base, but it does not mean that. It's more like, if we wanted to write it a little bit clearer, we would maybe write that it's 40 times e to the 0.6x power equals 240. So that 40 is like a separate coefficient. It's 40 times the exponential. So before we start rewriting or anything, we need to divide both sides of our equation by 40. And that would reduce to 1. So we have e to the 0.6x power is equal to 6. 240 divided by 40 is 6. And now we can rewrite it. So as we rewrite this equation, it's going to be a log base e. So we write the log with whatever the base is, the base stays the same, of 6 is equal to 0.6x. Well, we often don't see, or I guess that was a weird way to say it, but we don't often see a log written with a base e, because hopefully you remember that that is usually written as the natural log. The natural log of 6 is 0.6x. Well, our calculator can calculate that natural log quite easily. So we have the natural log of 6 is my calculator tells me it's about 1.792. That's equal to 0.6x. So if I want to solve for x, I just need to divide by 0.6. So we come up with the solution that x is equal to 2.986. If you ever were wanting to make sure your answer is correct, you could always substitute it into the initial equation and just see if it actually works. Okay, last exponential one that we're going to look at. So we have e to the negative x power plus 1 is equal to 10. So again, it's not ready to rewrite the way it is. We've got this a little bit extra right here, this plus 1. So we want to first subtract that. So make sure as you're doing these that before you try to convert them to another form that you make sure that they are simplified a bit if they need. And now we have e to the negative x equals 9. So if we rewrite that equation, it would be a log base e. And I usually don't even write the log base e. I usually go straight to writing natural log. But if it helps you to make sure you're doing it correctly, go ahead and write that log base e of 9 is equal to negative x. So we have the natural log of 9 is equal to negative x. Sometimes this throws people for a loop when we've got a negative x here. It seems a little weird. There's lots of ways that you could think of this. I'm gonna think of it as a coefficient of negative 1, so I'll divide by negative 1. So this would be the log, so the natural log of 9 divided by negative 1 is just negative natural log of 9. That's now equal to x. So this would be like an exact answer. It's a number, negative natural log of 9. If I wanted to know the decimal approximation, I could calculate that in my calculator. And it would be negative 2.197. That would be a decimal approximation. Okay, so that's it for our exponential equations. We also can solve logarithmic equations. So we're going to look at some log equations now. So our first question is, for what value of x is this equation true? Log base 4 of x is equal to 8. The strategy we're going to use as we solve log equations is that we're going to rewrite them as exponentials. So we have something that looks like this. If we turn it into an equation that looks like this, an exponential equation, then we can easily solve it. So we have here a base 4. And if we rewrite this equation, it will be 4 raised to the power 8 is equal to x. And essentially, we're pretty much done. We just need to calculate what 4 to the 8th power is. And that happens to be 65,536. So rewriting a log as an exponential can solve the equations pretty easily. So let's work on these two. We have the log base 4 of x plus 3 is equal to 2. If we rewrite that equation, it would be a base 4 raised to the power 2, so we're writing it as an exponential, and that would be equal to x plus 3. Well, 4 squared is exactly 16, so 16 is equal to x plus 3. And to solve for x, we would just subtract 3. So we have 13 is equal to x. One more of these. We've got log base 5 of x minus 4 is being raised to the 6th power. And we have that equal to 18. So as we look at this equation, you might notice that it has a 6th power. Well, one of the cool features of logs, one of the properties of logs, is that you can bring powers to the front as a coefficient. So this is the same as 6 times the log base 5 of x minus 4 is equal to 18. So to solve this, we want to have the log just a log with no coefficient. So we want to divide both sides of our equation by 6. So it reduces here, and we have the log base 5 of x minus 4 is equal to, and 18 divided by 6 gives us 3. So now we have that log equal to a number. We can rewrite it as an exponential. It will be 5 raised to the 3rd power is equal to x minus 4. Well, 5 to the 3rd power is just a number. 5 to the 3rd power is the same as 125. So that's equal to x minus 4. And then finally, we can add 4 to find the solution that 129 is equal to x. Let's look at another one. 3 times the log of negative 5x is equal to 0. Well, 3, the coefficient 3 here, we could go ahead and divide both sides by 3. So we get those two reducing. We have the log of negative 5x is equal to, and 0 divided by 3 is 0. So now we have the log ready to go. We can rewrite it, except a lot of people get stuck right here when they need to rewrite it because uh, they're just not sure how to rewrite this. And the reason that it might stump you is because this is a log in which the base is not physically written there. We understand and we know, hopefully, and you remember if I remind you that an log log is base 10. So the base isn't written there, it's understood. So it'll help if you'll write your base 10 in when you get to the step, so that you can see when you rewrite it, it's going to be 10 to the 0 power equals negative 5x. It is base 10. So now that we have this written as an exponential form, it's fairly easy to solve. Well, 10 to the 0 power is just 1. So we have 1 is equal to negative 5x. And then to solve for x, we just need to divide both sides of our equation by negative 5. And that leaves us with the result negative 1/5 is equal to x. That's fine. If you want to write it as a decimal, that's fine as well. It's just negative 0.2. Either of these is fine. Okay, another equation. The natural log of x to the 4th power minus 3 is equal to 25. So there's not any grouping here, so it's understood that the argument of the log is just the x to the 4th power. So we'll start this problem by adding 3. So we have the natural log of x to the 4th is equal to 28. Well, one of the properties of logarithms is if we have a log of something raised to a power, we can bring that power down as a coefficient. So we have 4 times the log of x is equal to 28. And now we can actually divide both sides of our equation by 4. So we have the natural log of x is equal to 7. It's a really good 4 there. And we've got the log, we've got the equation simplified to the point where we could rewrite it. And again, sometimes people get stuck here because the base is not physically present. But we know a natural log ln is base e. So if we rewrite this, it would be e to the 7th power is equal to x. E to the 7th power is just a number. If we wanted an exact answer, that would be the exact answer. But if we wanted a decimal approximation for that, we would go ahead and use our calculator. Remember, there's an E button. You would use the second button and the ln on most calculators, or sometimes there's another E somewhere over by the pi button. So E to the 7th power is equal to 1096.633. So this would be a decimal approximation of E to the 7th. Either of those would probably be okay. All right, so what is log of negative 5? Well, if you try to evaluate that in your calculator will tell you error. It will tell you, depending on the calculator, it might tell you that there's a non-real answer, or it might say error, domain error. There's a lot of things that it might say, but the bottom line is that your calculator can't calculate the log of negative 5 because log is not defined for negative numbers. It's not inside the domain of the log function. It's very similar with radicals and with some rational equations. You may have domain restrictions. You may have x values that just don't work with those functions that cause errors. And we've seen those a couple of times so far this year, and logs fall into this category of possibly having extraneous solutions. So it's important to check your answers when you're solving a log equation. Now, if you have just a simple log equation, you're not going to have an extraneous solution. It's going to work fine, and you could check it every time. It'll be fine. The extraneous solutions and checking for extraneous solutions becomes really important when you have a couple of logs in your problem and you're condensing them. And that's where you might run into false solutions coming from your algebra. So for the rest of these equations that we're working with, we are going to check for extraneous solutions. So this first equation, the log of x minus 7 minus the log of x plus 2 is equal to 1. This equation has a couple of logarithms, and in order to use our strategy of rewriting the equation of as an exponential, we've got to condense it into one log. So the log of x minus 7 subtract the log of x plus 2. We have our log property that tells us if we have a log and we subtract another log, that's the same thing as the log of the quotient of the argument. So it's the log of, in this case, the way I have it written, a over b. So in this case, this would be my first part, and this is going to be that second part, the b. So it'll be the log of x minus 7 over x plus 2 is equal to 1. And again, I just used this log property to condense it. So now if we rewrote this equation, and now we can rewrite it, it still looks a little bit complicated, and it is complicated. This is not an easy problem, but we need to remember before we rewrite it that this is a base 10 logarithm. So when we rewrite it, it would be 10 to the power 1 is equal to this fraction x minus 7 over x plus 2. Well, 10 to the power 1 is just 10. Anything that is raised to the power 1 is just itself. So we could rewrite this, I guess, if we wanted to, as 10 equals x minus 7 over x plus 2. And our ultimate goal here is to solve the equation for x and to find out what x is equal to. Well, right now we have an equation that is part of it, at least, is a fraction, so it's technically a rational equation. Anytime you have a fraction in an equation and you don't want to have a fraction, the best thing to do, or one thing to try, is multiplying both sides of the equation by the denominator. So if we multiply by x plus 2 on both sides of our equation, we end up with the equation 10 times x plus 2 is equal to, and on this side, those x plus 2's reduce, so we're left with just the x minus 7. We could distribute on the left here, so we have 10x plus 20, and that's still equal to x minus 7. Our ultimate goal is to solve for x. We need to get those x's together. Let's subtract x from both sides. It leaves me with a 9x. And it probably would be logical to move this 20 over to the other side. So we have 9x is equal to negative 27. And then finally, all I need to do is divide by 9. So we end up with x is equal to negative 3. So this is a complicated equation. We do all this algebra. We condense, we multiply by denominators, we just manipulate our equation. We get x is equal to negative 3, and we need to check that answer and make sure that it actually works. So if we substitute negative 3 into our original equation, negative 3 for x, we end up with the equation. I'm going to move this up a little bit and write it above it. We end up with the equation the log of negative 10 minus the log of negative 1 is equal to 1. Well, if you try to evaluate the log of negative 10 in your calculator, it does not work. It gives you an error. We can't take the log of a negative number. It's not in the domain of log. So it's not working. It doesn't work. It doesn't give me the answer. Now, the reason that the algebra turns out the way it does and it tries to make you think it's an answer is that when we condense this, this becomes the log of negative 10 divided by negative 1, which is just the log of 10, which is in fact equal to 1, and it would work. But our original equation was not that. That was a step we chose to take. So it doesn't work. This gives me an error in my calculator. This gives me an error. And so this is an extraneous solution. So this equation does not have a solution. No solution. That's a lot of work, I know, to get no solution, but it is what it is. Okay. We're going to do a couple more that involve condensing, and these are difficult. Stick with me. I know you can handle it. You'll be fine, but they are difficult for sure. So in this equation, we have the log of base 3 of x plus 7 is equal to 2 minus the log base 3 of x minus 1. So our logs currently are on two separate sides of the equation. So we do want to be able to condense them. So in order to condense them, we need to get them together. And it is fine to go ahead and add a log to both sides of the equation. Whoops, not x minus 3 though. So we're going to add the log there and here. And then these two would sum to 0. So we've got, if I rewrite my entire equation, I had originally the log of x plus 7. I'm adding to that the log base 3 of x minus 1. And at this point, it's all just equal to 2. The 2 is the only thing left because that log reduced. And I wrote 3. Wow, go team. I'm saying 2, but I'm writing 3. Equal to 2. All right, so now I can condense my two logs. And if you remember, our log rule with addition is that if I have a log and I'm adding it to another log, it's the same as the log of the product. So I need to take my two arguments. I have an x plus 7 and I have an x minus 1, and we have to multiply them. So it's the log base 3 of an x plus 7 times an x minus 1. And that's still equal to 2. All I did was condense it into a single logarithm. Well, I'm going to go ahead and multiply these binomials out. So this is going to be still a log base 3. I'm just trying to simplify my argument a little bit. And if I multiply this out, I have an x squared. I have a negative 1x and a positive 7x, so that's a 6x, and I have a negative 7. Still equal to 2. And now we're going to rewrite this as an exponential equation. So it would be the same as 3 to the second power, and that's equal to x squared plus 6x minus 7. Well, 3 squared is the same as 9. And what we have here is a quadratic equation. We have an x squared term and an x term. It's a quadratic. It's going to have two solutions, and we can find those two solutions hopefully by factoring, or if not, may have to resort to the quadratic formula. So if we subtract the 9 from both sides, and we do that because in order to try factoring, or in order to try the quadratic formula, we have to have our equation equal to 0. So we have an x squared plus a 6x, and now it's a negative 16 constant at the end there, so minus 16. So now if we try factoring this, we're thinking of factors of negative 16, and we need them to add up to 6 in order to factor this. So it would be an x plus an 8 and an x minus 2. Well, those two factors give us our two solutions. X could be equal to negative 8 or x could be equal to 2. So these are two potential answers. But remember, when we have logarithmic equations like this, we have to check our answers to make sure that they work. Our original equation was the log base 3 of x plus 7 equals 2 minus log base 3 of x minus 1. If we substitute in our value negative 8 here, and this could be a mental check, you wouldn't need to write it out. This would be negative 1, and this would be negative 9. And we can't take the logarithm of a negative number. These would both give me errors in my calculator if I tried to evaluate them. In some ways, it's similar to a square root. You can't have a negative here. Same with logs. You can't take the log, whoops, you can't take the log of a negative number. So if you end up with log of a negative number here in the argument, that's when your calculator is going to give you errors. There's no way to evaluate it. It's not in the domain of log. So the negative 8 didn't work. That's an extraneous solution. If we test the solution 2, we would have that the log base 3 of 2 plus 7 is 9 is equal to 2 minus 2 times the log base 3 of, and we would have 2 minus 1, which would give us a log of 1. And that's fine. In fact, we could check this in our head. Log base 3 of 9 is 2, so that's saying 2 is equal to 2 minus log base 3 of 1. That's asking me what power of 3 gives me the answer 1. That's 0. So it's just an equation saying that 2 equals 2 minus 0 if we substitute in x equals 2. So this one does work. Again, your check can be a mental check. You're checking to make sure that you don't have the log of a negative number. That would be an extraneous solution. Okay, I know these take a long time. I know they're hard. We're going to do one more of these type. Log base 2 of x plus log base 2 of x minus 2 is equal to 3. So if we condense this, and this one is ready to condense here, our first argument is x, and our second argument is x minus 2. So this would be the log base 2 of, our logs are being added. So we would go ahead and multiply those arguments. Log base 2 of x times x minus 2 is equal to 3. We could distribute that argument so that we have x squared minus 2x. All right, so now we're ready to rewrite it. If we rewrite this, our base is 2, so it'll be 2 to the third power is equal to x squared minus 2x. Well, 2 to the third power is 8, so we have 8 equals x squared, whoops, minus 2x. And this is a quadratic equation. It has an x to the second power. We could solve this by attempting to factor it. Before we attempt to factor something, we want to go ahead and get it equal to 0. So we're going to subtract 8. So we have 0 equals x squared minus 2x minus 8. If we factor that, we end up with the two factors x minus 4 and x plus 2. Remember, we think of factors of negative 8 that add up to negative 2. So our two potential solutions are 4 and negative 2. We need to check those. Well, our first part of our equation is the log base 2 of x. If we put 4 in there, it's going to be handy dandy fine, perfectly okay. In fact, it's equal to 2. If we substitute in negative 2, that's an error. So for sure the negative 2 doesn't work. Our other log is log base 2 of x minus 2. If we substitute our x value 4 into that one, it does also work. It'd be the log base 2 of 2. So our solution x equals 4 is a good one. And so we have the solution x equals 4. Good times. Okay, there is one more type of logarithmic equation. It's actually one of the easier ones to solve, but sometimes people forget about this type. But we have logarithms have a one-to-one property. And what that means is that if you have the log of something and it's equal to the log of something else, if they're the same base, those two things have to be equal to each other. So it's saying if the log of A is equal to the log of B, it just means A has to equal B. So in this first example, we have the log of 11x minus 9 is equal to the log of 8x plus 42. And they're both base 4, so they're the same base. And that means the 11x minus 9 has to be equal to the 8x plus 42. We can solve this without too much trouble. You're all experts at things like this. If we subtract the 8x, we end up with a 3x. And maybe we want to add that constant to the other side. So we end up with 3x is equal to 51. And if we divide by 3, we come up with the solution x equals 17. And if you do a quick mental check there, you'll see that that works just fine. The second one is a little bit more complicated. It's not as complicated as the ones we were just doing a moment ago, though. We have the log base 6 of 3x plus 14, subtract the log base 6 of 5, and it's equal to the log base 6 of 2x. Well, we do have two logarithms on the left side of that equation, but we could condense them into one logarithm. So we have the log base 6 of 3x plus 14 divided by 5, because it's subtraction here. Subtraction of logs becomes the log of the quotient. And that's equal to the log base 6 of 2x. Well, I have a log base 6 equal to a log base 6. The only way that that can be true is if the two arguments are equal to each other. 3x plus 14 divided by 5 is equal to 2x. Well, we have an equation that we would like to solve, and our equation has a fraction. If we have a fraction in our equation that we would really rather not have, the way that you deal with that is that you would multiply by your denominator. This time our denominator is 5, so we multiply both sides of our equation by 5. That one reduces. So we have 3x plus 14 equals, and 2x times 5 gives us a 10x. This equation is not too hard to solve at this point. We've done the hard work. So if we subtract the 3x from both sides, we have 14 is equal to 7x, and if we divide by 7, we get the result that x is equal to 2. And you can do a mental check there to make sure that it works, and it shouldn't give us any problems. 3 times 2 is 6. I'm just thinking about this one. Add 14 gives me 20, so this would be a log of 20. The only other place x shows up in our equation is here. This would be the log base 6 of 4. So it works just fine. We don't have to worry about that being extraneous. All right, so we started with exponential equations that looked like this. To solve them, we turned them into logarithmic equations. Be careful when you're dealing with logs that don't have the base written. Remember, log log is base 10, ln log is base e. The next thing we did is dealt with logarithmic equations, and the way that we would solve those is to turn them into exponentials. Sometimes you have two logarithms that you need to condense in order to make that happen. And then don't forget the easy peasy type. If the log base b of a is equal to the log base b of b, that just means that the a has to be equal to the b. So that is solving. We're going to look at two equations that have some context, and then we'll be finished. So our question is, if left unchecked, a new strain of the flu virus can spread from a single person very quickly. The number of people affected can be modeled using the formula P of t equals e to the 0.22 t power where T represents the number of days the virus is allowed to spread. P here would be the number of people affected, so how many people have the flu. So question A says, how many people will be infected after 2 weeks? Well, our equation here has a T in it, which is representing time, and specifically time is measured in days. So this first equation is saying how many people, so it's saying what is P, how many people will be infected after 2 weeks. So that's saying if T is 14. 2 weeks would be 14 days, and we are measuring our time in days. So we are wanting to know what is P of 14. If I plug 14 in for T, well, that would be equal to e to the 0.22 times 14 power. And if we use our calculator to evaluate that, we find that P is equal to 21.75. Now we're finding a number of people, so we'd probably want to round to the nearest person. And, you know, probably in this case, even though it's a 0.75, you would probably say 21 people are infected. That it hasn't reached 22 yet, but 22 would be okay for me, at least. If you rounded it to 22. So 21 or 22 people. Second part of this, though, is not asking the same thing. It's saying how many days. So it's asking us to find T. So how many days will it take for 1,000 people to be affected? It's giving us the P value. So if we set up our equation, it would be 1,000 is equal to e to the 0.22 t power, and we're trying to solve for t. If we rewrite this equation, a lot of times when we rewrite, we get used to seeing the exponent first, the exponential part first, and the answer over here. So when you're rewriting something where it's sort of reversed, make sure you're careful about it. It would be the natural log. So remember, natural log is log base e. So it's the natural log of 1,000 is equal to 0.22 t. If you're writing it from this form here, you just need to remember that the answer to the log is the power of the exponential. So you could write natural log of 1,000 equals 0.22 t. If you remember, just be careful sometimes. So natural log of 1,000 is something our calculator can easily calculate for us. So this would be 6.908 is equal to 0.22 t, and then we would just need to divide by that 0.22. And that would tell us that t is equal to 31.4 days. So about a month or so, and you'd have 1,000 people infected with that flu. Okay, one last problem. It is in context again. This time we have a logarithmic equation to deal with. So we have in chemistry, pH is a measure of acidity of solutions, and it's given by the formula the pH is equal to the negative log of H plus, which H plus is the hydrogen ion concentration. So part A says, what is the pH? So we're trying to find pH. What is the pH of a solution if it has a hydrogen ion concentration of 3.16 times 10 to the negative 7th moles per liter? Well, pH is equal to the negative log of the concentration of hydrogen ions. Whoops, not 7. Sorry. 3.162 times 10 to the negative 7th. And we can use our calculator to evaluate that. You just type it in as it is. And when we evaluate that, we find that the pH of this solution is about 6.5. So it's slightly basic. 7 is neutral. It's okay if you don't know that, but if you were in chemistry, you might recognize that. So part B, though, is quite different. Part D says find the hydrogen ion concentration of a solution if it's known to have a pH of 4.2. So it's telling us the pH, so that is going to get, that value 4.2 is going to go where pH is in the equation. So we have 4.2 is equal to the negative log of the hydrogen ion concentration. So we're trying to solve for this value. You can think of this as our x if you want. Or if it helps you, you can even put an x there instead of the h plus. So if we solve this equation, we want to get that log in the most simple form. We just want a plain old log. And so right now it's a negative log. We'll divide by -1 in order to make that a little simpler. So negative 4.2 is equal to the log of the hydrogen ion concentration. And now we can rewrite this. Well, this is a base 10 log. Log log, remember when it's not written there, the base is not written, it's base 10. So this would be, if we rewrote it, 10 to the negative 4.2 power is equal to the hydrogen ion concentration. And that's what we're trying to find. Like, this is our goal, so we just need to tell our calculator to evaluate that for us, 10 to the negative 4.2 power. Now, you might not be super familiar with scientific notation. It's usually taught in school. I'm not sure which grade in Utah. I should look that up. But your calculator, when you type that 10 to the negative 4.2 power, may display something like, you know, I'll write out a couple of decimals here. And then it has a capital E and a -5. So that's giving you your answer in scientific notation, which is, it's giving you your answer essentially in this form, but instead of using times 10 to the power, it uses that E symbol, that capital E symbol. So this would be the same as 6.3, I'm going to put 6.310 if I round that, times 10 to the -5th, and that would be moles per liter of hydrogen ions. Okay. And that's it. That's solving the equations. We'll practice more on review day. The test for A-Day students, well, the review for A-Day students will be Tuesday. Test will be on Thursday. For B-Day students, the test will be on Friday, with the review being on Wednesday. If you didn't take your quiz, you can do that on the review day, or if you took your quiz and were not happy with your score, you can retake that also on review day. So that is it. If you need some help solving these equations or with any of our other log topics, please come in as soon as you can. The test is going to be here before you know it, and I'd like to help you get squared away before the test, and that way you can avoid having to try to do a retake.